Hello dear students, welcome back to the series of lectures on the integer theory with course code MMTC 202. So today in this lecture we will try to extend the notion of Lebesgue measure on Rn. Okay. So the topic of the lecture is Lebesgue measure on Rn. Lebesgue measure on Rn. Lebesgue measure on Rn. Lebesgue measure on Rn. So first we fix some notations. So let me denote this. Let Sn denotes this collection of the product of n copies of semi-closed interval is its product. I runs from 1 to n ai bi, where these ai bi's they are just real numbers there. So it's actually a collection of subsets of Rn. It's a collection of subsets of each member is actually the subset of Rn. So where this AIBI this product I runs from 1 to n AI BI is the product of n copies. It's A1 B1 cross A2 B2 cross AN BN, and it's equal to this set of n tuples. It's equal to the set of n tuples. It's x1 x2 so on xn, where these xi's they lie between ai and bi, where this ai less or equal to xi less than bi. I varies from 1 to up to n. If each ai, if ai is less than bi for all I. Okay. So this set is just it is a collection of n tuples like this. In case each ai is less than bi, a1 is less than b1, a2 is less than b2, and so on and so forth, an is less than bn. And in case there is some I size that ai is greater or equal to bi, then it's equal to the null set. Then this product is the not it is the empty set. If for some I ai is greater or equal to bi. So that's this product of the n copies of these semi-closed intervals. So it means that this Sn it also contains the empty set as well. And in our one of our previous lectures, we have shown that this collection of the product of n copies of semi-closed intervals forms a semi-ring on Rn. So then Sn is a semi-ring on Rn. So for let's I will give an example of these intervals. Say I will fix for n equal to 3. Say so if you want to write this interval 1 2 cross say 5 6 cross product say 2 and 9. So this is the set of 3 tuples x1 x2 x3 with this 1 less or equal to x1, 1 less or equal to x1 less than 2, and then we have this 5 less or equal to x2 less than 6, and finally we have this x3 which is 2 less or equal to x3 and less than 9. Okay. So this is the set. And if one of them is greater, then suppose we have this one 1 2 cross product is say let's right here say say this one 2 and say 1 2 and 2 suppose cross 3 5. So this is a since this is here equality holds for one I, this 2 is equal to 2 and this will be equal to the empty set. So that's an example. And this SNS summering is already shown in our lectures when we have discussed the Lebesgue measure on R, where we have shown that this collection of the semi-closed, this collection of the product of n copies of semi-closed intervals of R forms a summering on Rn. So this is summering. Let's define a set function. Define a set function. Lambda n. Okay, let's define set function lambda n from Sn to 0 to infinity by lambda n of the empty set is 0. I will set this as 0, and the lambda n of the non-empty set. Non-empty set means this the product of k copies, product of n copies I runs from 1 to n. Ai bi is equal to the product of the lengths. Its product I runs from 1 to n bi minus ai. If these ai's, if ai is less than bi for 1 less or equal to I less or equal to n. So in case there is reverse inequality for some I, then the set is the empty set, and this lambda n of the empty set is equal to 0. And in case for each I1 ai less than bi, then the value of this set under the lambda n it is the product. It's the product. So we shall in our next theorem we will show that this lambda n it's actually the Lebesgue measure on, it's the measure on Rn. Okay. So that's our theorem. The set function lambda n, the set function lambda n from Sn to 0 to infinity defined above is a measure. Defined above is a measure. And it called the Lebesgue measure. Called the Lebesgue measure on Sn. Called the Lebesgue measure. Called the Lebesgue measure on Sn. Proof. To prove the result, we use induction on n. Okay. To prove the result, we use induction. We use induction on n. So for n equal to 1, we show that this one is a measure space. S1 lambda 1 on this R is a measure space. So it's X notation is the different actually. This is R, then we have the summering S1, then lambda 1. This is a measure space. This is a measure space. So it's already done actually. This lambda 1 here, the lambda 1 is here. Here lambda 1 is a function from S1 to 0 to infinity defined by lambda 1 of empty set is 0 and the lambda 1 of the semi-closed interval, because here the case n is equal to 1, so where in real line r it's equal to b minus a. So it has been already shown that this is already done. Okay, this is already done. This. So this is already done. Okay, this is already done. Already done. So therefore the result holds for n equal to 1. Therefore the result is true for n equal to 1. Now assume inductively that the result holds for some n. We show that we show that it also holds for n plus 1. That means this r n as n lambda n is a major space. It's given by induction here is a major space, and we show that this one is a major space. We show that r n plus 1 as n plus 1 and this lambda n plus 1 is a major space. Is a major space. Okay, this is a major space. So clearly this one by definition of lambda n plus 1, by definition lambda n plus 1 of the empty set is it's always taken to be 0, it's equal to 0. So why now now we just prove that this is sigma additive. Therefore it is sufficient to show that therefore it is sufficient to show that lambda n plus 1 is sigma additive. So let's take any disjoint sequence in Sn plus 1. Let's take these disjoints. Let ai cross ai comma bi. It's this is a sequence in be a disjoint sequence in be a disjoint sequence in. So what's Sn plus 1 actually? Sn plus 1 is the product of n plus 1 copies of semi-closed intervals. So this AI it's the product of n copies, and this is the n plus 1th copy. So it's actually the product of n plus 1 copies of semi-closed intervals. Okay, semi-closed interval. And this sequence is a disjoint sequence in Sn plus 1 such that the union I runs from 1 to infinity ai cross ai bi, it also belongs to Sn plus 1. So that means this union is also the product of n plus 1 copies of semi-closed intervals. So let's take this as let a cross ab be the union. So that means this A is actually the product of n copies of semi-closed intervals, and this is the n plus 1th copy. So that means it is the product of n plus 1 copies of semi-closed intervals. And let's take this as the union, okay? Because it belongs to Sn plus 1, sorry, Sn plus 1. Ai cross ai bi, okay? So we need to show that this we show that we show that this Lebesgue measure of this one this union, sorry, this union Lebesgue measure of this union, this is the union, it's equal to the summation I runs from 1 to infinity, this one Lebesgue measure of AI cross AIBI, okay? Semi-closed into AI cross AIBI. Okay, that's this is the Lebesgue measure, okay? And that is what is this actually? It is the this by definition it is a product of these lengths of the n plus 1 intervals. So it's actually the product of the lengths of n intervals in the product of the length of the n plus 1. That's we need to show that this one Lebesgue that product of the this one, it's actually lambda a actually, because lambda n of a is the product of n copies of semi-closed intervals, and lambda n of a mean is the product of the these n product of the lengths of these n intervals. Okay, so this is actually lambda n of a into this one it's the length into b minus a. Okay, we need to show this. This is actually, this is here the product of n plus 1 copies, lambda n plus 1 of a cross ab mean is the product of the lengths. Okay, so they are n plus 1 copies, so it is the product of the lengths of n plus 1 copies of the semi-closed intervals. Okay, so this we need to show this is equal to summation I runs from 1 to infinity. So again here it's this is the Lebesgue measure. This is the set function by definition. It is the product of the lengths of n plus 1 copies. That's the product of the lengths of n copies into the product of into the length of the n plus 1th copy. So it's like this actually. It's lambda n of ai, lambda n of ai into bi minus ai. So this we show, name it star. Actually we need to establish star actually. Okay, so to prove star to prove star we had this a cross b. It's the disjoint union of a cross b, a cross ab. It's the disjoint union I runs from 1 to infinity. That's this union is equal to a cross ab. This is our notation for this union. It's ai cross ai bi, and they are disjoint. So therefore what's the what's this characteristic function of this a cross ab? It's a characteristic function of the disjoint union. That's summation I runs from 1 to infinity into the characteristic function of these sets ai cross ai bi. Okay, now for each fixed x now for each x belongs to for each x for each, actually we have to use the induction. We have to use the fact that Sn, that Rn, lambda n, and this Rn, Sn, and lambda n is a measure space. So for this I will take a point x equal to x1, x2, so on, xn in Rn, and take a point t belongs to R. P belongs to R. Then this holds. Then this holds. You can easily verify it. Then this holds. Chi ax is equal to, because a is a subset of Rn and x is a point of Rn, so it's a characteristic function of the subset of Rn. So x must be in Rn into chi ab. AB is a subset of what? It's subset of R. So this is the characteristic function of the subset of R, and T is a point of R. This is equal to This is equal to summation. We need to show that this is equal to summation I runs from 1 to infinity chi aix is our subset of Rn into correct function of the ai bi of t. So we need to establish this one. Okay, name it, say, double star. So let me see this. If suppose x belongs to a and t belongs to ab, suppose, then chi x is 1, chi ab of t is 1. Okay, this side is equal to 1. But now we need to verify this side should also be equal to 1. Now since x is in a, t is in ab, therefore x comma t belongs to a cross ab, belongs to the Cartesian product a cross ab. But this a cross ab, you can see it here, this a cross ab, it is this disjoint union, so it means it belongs to exactly one ai cross ai comma bi. So whenever it belongs to exactly one ai cross ai comma bi, so that means this x, there is a unique I size that x belongs to ai and t belongs to ai comma bi, so this must be equal to 1. So that means in this sum exactly one term is equal to 1 and the rest of the terms are equal to 0. So that means this side is also equal to 1. So that's simple. Now second case, you can think about this. If x is not in, if x is not in a and t is not in ab, or either one of them, x is not in a or t is not in ab, then x comma t is not in a cross ab. Obviously that's trivial, because we know that x comma y belongs to the cross product if and only if x belongs to the first set and y belongs to the second set. But when x comma t, when either x is not in a or t is not in ab, it means that x comma t is not in a cross ab. So when x comma t is not in a cross AB, that means that x comma t cannot be in the union, because a cross AB is equal to the union. It means that that x comma t is not in any ai cross ai comma bi. So which means that these x, these x's, there does not exist any I such that x belongs to ai and t belongs to ai comma bi, because otherwise that x comma t should be in the union, because if there is some I such that x belongs to ai and t belongs to ai comma bi, then x comma t must be in ai cross ai comma bi, which means that x comma t must be in the union, and which gives x comma t must be in a cross ab, which is not the case because x comma t is not in this set. So that means whenever x is not in a or t is not in ab, then x comma t is not in the set, and that means there does not exist any I such that x belongs to ai, t belongs to ai comma bi, which means that each term of this sum is equal to 0 and this side is also equal to 0. So both the cases are done. If both x belongs to a, t belongs to ab, then both sides are equal to 1. And if either x is not in a or t is not in ab, then both the sides are equal to 0. So that I leave this for you to write those steps. Okay. So this is this equality holds. This equality holds. Now I will try to generate the function of real numbers t from this. I will fix this x. Okay. I will fix x and make it as a function of t only. So fix x, fix x equal to x and x, so on, x in, okay, fix x equal to this point, it's the n tuple, and let's define this function, and let's define this function, function of t, okay, which is equal to summation I runs from 1 to k, I runs from 1 to k into the characteristic function of aix, where this x is fixed. You can treat this as constant here. And then we have characteristic function of ai comma bi in t. So this is the step function. These are the scalar. These are those small ai's actually, because this x is the constant. So you can treat these as small ai. It's summation I runs from 1 to k small ai into characteristic function of ai comma bi into t. So this is step function, simple function with the measure of each set is finite, because measure of each set is the length of the interval, that's bi minus ai, which is a finite number. So then this phi k is a sequence of then phi k is a sequence of step function, is a sequence of step functions, is a sequence of step functions, such that when k is approaching to infinity, this, what's this? This will be equal to, such that this, it's an increasing sequence. You can verify easily, because if for say for say k equal to 2, this is sum of the two terms. For k equal to 3, it will be the sum of three terms, and each term is actually non-negative, so it's monotonic increasing. And this limit, if I see the limit with respect to k, this limit k is approaching to infinity. What's this? This is summation I runs from 1 to infinity chi aix, okay, chi aix into characteristic function of ai comma bi of t, and that's equal to that summation. That summation is equal to the chi ax. That's this here. Chi, this sum is equal to chi a of x into chi a b of t. Okay, this sum. Okay, you can see it here. This sum. Okay, this summation. Okay, this summation is equal to chi x into chi a b of t. Okay. So this phi kt, it increases to this one, huh? This function chi x into chi a b of t. Okay, this is true for each x. Okay, for each x and for each fixed x. This is true for each fixed x. For each fixed x. Okay, this is a function of t, but this holds for each fixed x. For each fixed x belongs to Rn. Okay, for each fixed x belongs to Rn. Now, by inductive hypothesis, look at this line. This one, this increases to this. What's phi kt? Phi kt is this this summation. So if I apply now, this is this you have take the limit with respect to k, but with respect to the variable t. But now if you vary the x and fix this t, then you have this summation I runs from 1 to k chi ai of x, which is the characteristic function of subset of Rn. And this is, I want to say that sin is by induction, sin is by induction, sin is by induction, sin is by induction, sin is by induction. This Rn, Sn, and lambda n is a major space. This is a major space. Is a major space. So therefore by applying the same result, therefore this whole is summation I runs from 1 to k, summation I runs from 1 to k. This is bi minus a. Now this is now fixed, bi minus a into the Lebesgue measure on Rn. Okay, this will increase to b minus a into the Lebesgue measure of a, into the Lebesgue measure of a. So look at this stuff. This is from double star actually. Now if I write this phi kt as this series, then you can apply the integral. Then this is phi kt. Okay, phi kt. We have to write one more step here. That means we have to apply the integral as well. Integral of this with respect to t is actually okay. This is not correct here. I have to apply the integral here actually. Sorry, with integral over because this R1 this S1 lambda 1 is a major space, so I have to apply the integral over R actually here. So this one you have to apply the integral over R. So whenever I apply the integral over r, so this phi kt, it increases to the function that's okay. This phi kt increases to this phi kt, this is step function, and it increases to, so that step was actually correct, but I have to add one more step here. This increases to that series is equal to chi ax into chi abt. Okay, now this is a step function with respect to t. This increases to this. Now the integral of this will increase to integral of this with respect to t. But what's the integral of this? What is the integral of this with respect to t? So therefore the integral of phi kt increases to the integral of this function chi ax into chi ABRT. But this gives, what's this integral actually? Integral of phi kt, it's the integral of this, that's the sum of the integrals, but you are integrating over the variable t, so it is equal to summation I runs from 1 to k, this is fixed here, chi a x into this one is equal to bi minus a, because the integral of this function is equal to the Lebesgue measure of this set, which is the length of the interval, and that will increase integral of this is a constant, so this will be equal to chi x, it's constant, into the Lebesgue integral of this, which is equal to the length of the interval b minus a. So that's our double star. Okay, now I vary x, I will do integration with respect and and since this the result is true for n, so these are the this is the correct, this is now the stuff function, this is now the stuff function of in Rm. Okay, it will increase to this stuff function in R. So I can apply the result, I can apply the induction hypothesis here, because I know that the result is true for this one. This one is a measure space, R and S and lambda n is a measure space. So therefore, this bi minus ai, it's not just a constant, and I apply here on the set ai here. Okay, so which is equal to the Lebesgue measure of the set will increase to b minus a times the Lebesgue measure of the set here. This integral of this stuff function will be equal to bi minus ai, it is just a constant, times the integral of this, which is equal to the Lebesgue measure of ai in the n dimension, and this will be equal to b minus a times the Lebesgue integral of this one, which is equal to the Lebesgue measure of a in n dimension, which is lambda n of a actually. Okay, so this is this is true now. So this one, from this we conclude that we are following. But what is this? This is the product of n copies of semi-closed intervals, length of the semi-closed intervals, and this is the length of the one of the interval length of the semi-closed interval, which this will be equal to Okay, that is that's we have this. This is actually the summation I runs from 1 to infinity. So this is actually this will summation I runs from 1 to k. This is just the Lebesgue n plus 1 of Lebesgue measure actually. Here this is lambda n plus 1. So this is lambda n into the one length, that's this actually lambda 1, which is lambda n plus 1 of ai cross ai comma bi. This will increase to the lambda n plus 1 of a cross a comma b. So that is this Lebesgue measure of this one is equal to summation I runs from 1 to infinity Lebesgue measure n plus 1 of ai cross ai comma bi. So that's this theorem. Now next we define interval of Rn. We define an interval of Rn. An interval of Rn, as we know that the intervals of R are either they are of this type, either a open interval or semi-closed intervals, or this one, or closed intervals. In fact, closed as well. These are called intervals of R, or intervals of R. So what are the intervals of Rn? Now we define the interval of Rn. An interval of Rn, an interval of Rn is any set of the form is any set of the form sorry here. Is any set of the form that we denote by I, which is equal to the product of n intervals actually. I where I is an interval of R. Is an interval of R. So these II, they may be semi-closed, they may be open, they may be closed, they may be any intervals. But if I will take the product of these and intervals, it is called the interval of Rn. And this interval of Rn, I is said to be the bounded open interval of this interval I, the interval I, which is equal to the product of n intervals, is said to be the bounded, is said to be a bounded open interval of Rn is said to be a bounded open interval of Rn if each ei is a bounded open interval of R, is a bounded open interval of R. And also, as in the Lebesgue, as in the one-dimensional case, we have shown that the Lebesgue measure of an interval is equal to the length, and it's same is true for the general case. If I is any interval, if I equal to product, they may be semi-closed, they may be open, is any interval of Rn, then Lebesgue measure of this I is equal to the length, is equal to this summation, this, sorry, it's a product, is equal to the product. That's this Lebesgue measure of the product actually. I runs from 1 to n. This Lebesgue measure is the Lebesgue measure on Rn now here. So this is equal to the product. I runs from 1 to n. So this is the length of I. Product of the lengths of the interval. For semi-closed intervals, if I is the product of all, if all these intervals are semi-closed intervals, then this is already done. This is by definition actually, yeah. But if say some of the intervals are semi-closed, some are open, or all are open, or all the intervals are closed, then the result is straightforward, as in case of the real line that we have already done. So this is true. Now next theorem, which is very important, we have a useful formula for Lebesgue outer measure. So useful. It's a useful formula for Lebesgue outer measure on Rn, that you need to verify yourself. This Lebesgue outer measure of any subset A of Rn is equal to infimum of that has been explained here in this in the book written by Albrecht. So it's equal to the infimum summation I runs from 1 to infinity, the Lebesgue outer measure of I, such that these each I is a bound, is an bounded open interval, such that each I is a bounded open interval, and this A is the subset of the union, bounded open interval of Rn here. Right? It's Rn here, and A is subset of the union. I runs from 1 to infinity I. So that's this formula. So the actual definition is you have to take the Lebesgue, you have to take the infimum summation I runs from 1 to infinity Lebesgue measure of the semi-closed intervals, where each I is a semi-closed interval. It's the product. It should be the product of n copies of semi-closed intervals by definition. But this formula precisely states that you can take these I's as bounded open intervals of Rn. So this is very simple. You have to apply the definition of infimum. Actually, you choose any epsilon positive, and you need to show that there exists a certain some sequence of bounded open intervals such that A is subset of the union, and the Lebesgue outer measure of A plus epsilon will be greater than that sum. Okay, so that you need to apply it. You need to apply the definition of infimum here actually. So this formula is very important, and we'll use this formula in future. So from now, the Lebesgue measure, the Lebesgue outer measure, from now, the Lebesgue outer measure lambda star generated by lambda will be denoted by lambda. So this will also be denoted by will be. So we don't write lambda star, we simply write lambda. Will denote the Lebesgue measure on a semiring as well as the Lebesgue outer measure generated by lambda. Okay. So the next theorem is which is the characterization of measurable sets actually. A subset E of Rn, a subset E of Rn is measurable if and only if for each epsilon positive, if and only if for all epsilon positive, there exists an open set O, there exists an open set O in Rn, open set in Rn, with such that E substuff O, this O covers E, and the Lebesgue measure of the difference O minus E is less than epsilon, is less than epsilon, is less than epsilon. Proof of the theorem. Assume E is Lebesgue measurable. Assume this E is Lebesgue measurable. Now, first consider the case. So, and consider the case, and let's consider this case, and let's take this case, and let this Lebesgue measure of E is finite. Okay, it's finite. Now, what's this Lebesgue measure actually? Lebesgue measure of any substuff Rn. It's here. It's the infimum over these actually. So that means for any epsilon positive, you apply this definition, this useful formula, and epsilon, let epsilon be any positive number. Then there exists a sequence, okay? There existed a sequence II of bounded open intervals such that this is substuff union I runs from 1 to infinity, and this holds, and summation I runs from 1 to infinity, so it's infinity here, 1 to infinity, not 1 to n, 1 to infinity, okay, 1 to infinity, Lebesgue measure of I is less than when I add this to epsilon infimum. This is actually infimum, and I am adding epsilon to this infimum. It will become created some element of that set where you are taking the infimum actually. So this holds. Let's take this set O. Let's define the set O. Let O is equal to union I runs from 1 to infinity II. Since each II is bounded open interval, therefore each II is actually open set of Rn, and the union of open sets is again an open set. Then O is an open set. Then O is an open set. Then O is an open set. Okay. Then O is an open set. Then O is an open set, and such that E substuff O, because O, such that E is substuff union II, which is equal to O, and this Lebesgue measure of O minus E, which is equal to Lebesgue measure of O minus Lebesgue measure of E. But this Lebesgue measure of O, this is actually less or equal to summation. This is less or equal to the summation I runs from 1 to infinity Lebesgue measure of II, because O is equal to the union II minus Lebesgue measure of E, minus Lebesgue measure of E. But this one, this difference is less than epsilon. You can see it from here. Okay, this Lebesgue summation of the Lebesgue measures of II minus Lebesgue measure of E is less than epsilon. Okay? This is less than epsilon. So this proves the one way of the theorem. Now we prove the reverse. But I have to take one more case, case second. In case first two, I have assumed that Lebesgue measure of E is finite. Now, if the Lebesgue measure of E is infinite, suppose it's infinite, then I define the sets. Then we define the sets. We define the following sets for each I. For each I. For each I. For each I, let bi is equal to. So I reduce this case to the case where this Lebesgue measure of the set is finite. Okay, for each I, let's define bi, which is equal to define the set bi, which is equal to x belongs to R and those elements of the n-dimensional space R and those n-tuples such that their distance from zero vector, okay, is less or equal to I. Okay, let's define this set. So their distance from zero is less or equal to I. And set this and define this, and AI is equal to E intersection BI. Then the Lebesgue measure of, then this implies Lebesgue measure of AI is finite. Lebesgue measure of AI is finite. So the Lebesgue measure of AI is finite and AI is measurable, and AI is measurable. Lebesgue measure of AI is finite and AI is measurable. And AI is measurable. Lebesgue measure of AI is finite and AI is measurable. So for each AI, I can find open set OI such that Lebesgue measure of OI minus AI is less than epsilon. I have to choose now epsilon to conclude the proof of this part. So I can choose the open sets OI for these EIs, because as in the case one where we have assumed that whenever the Lebesgue measure of E is finite and E is measurable, then for each epsilon positive, I can find open set O such that Lebesgue measure of O minus E is less than epsilon. Now here, this one is here.